Good morning, everybody. Today's our last day before exam 2. Can I get a show of hands of how many people plan on using their own non-graphing calculator during exam 2? You all have a calculator you're comfortable with, that you're not going to make mistakes because it's a new calculator to you. That's a lot of people. Okay? How many people would want to borrow a graphing calculator if I brought them? Okay. So I can bring 20, I think. I might even have a little bit more. So if you are playing with your calculator and really don't feel comfortable with it, borrow one of the ones I got, all right? We will not be allowed to use them on the ACS final exam. So if you're planning on that being your higher of your 2 final exam scores, then make sure you get comfortable using the non-graphing programmable calculator. Diana?
Will we even need a calculator?
I don't think you need a calculator on this exam. Sam, can you remind me? Okay. No calculations, I don't think, on this exam. But I want to make sure that you have something you're comfortable to use. I saw some people on exam 1 struggling because they were like, I don't know how to use this calculator. What's that?
Make me feel less stressed.
Okay, it'll make you feel less stressed having a calculator you're comfortable with. How do you add up AXC and steric number? It hurts. Okay, hopefully you don't need a graphing calculator for that. All right, so we're going to spend some more time talking about hybridization, how that relates to small and big molecules today, and then we are going to start talking about balancing of equations. Let's just do one thing. Homework, there was no pre-class quiz, but there was something you guys had to do. If you're still not seeing the things that I'm requiring you to do that are not due, please change your view. Instead of show me what's due, say show all assignments. If you show all assignments and look at the due date, it will show you things that are not graded because I think that's the big discrepancy that we've been running into. It doesn't show things that aren't graded, which I'm not happy about. But there was a PhET simulation I wanted you guys to go and play around with last night, and if you only looked at your graded assignments, you wouldn't have seen it. So make sure that you go back and change your view. Whenever you're looking at what's due tomorrow, always look at all assignments, please, and then sort by date, and you'll find the ones that are due. All right, if we're looking at this molecule, let's see what everyone says. I think we can show the results for that. So we have a discrepancy between 3 and 4 is our steric number. Double bonds count as 1 electron domain. And this is where if you're not quite comfortable with this, go back to the PhET simulation you did in lab. Add a double bond versus a single bond. See how that influences the molecular shape and electron pair geometry. You'll see that they're identical in the way they influence that. So that group, when you get to organic chemistry, sterics is how things occupy space. And so space filling is a way to look at sterics. So the steric number is how many things that occupy space are there. Okay, so we have a steric number of 3 around that carbon formaldehyde. Which of these, that's not short answer, could do short answer. Which of these describes the hybridization of that carbon? Dr. Dave, if you're not sure. Is that better? All right, I'm going to pick on Steven. What did you decide for the hybridization of the carbon, and how did you get there?
I said it was B.
Okay, you said it was sp2 hybridized. Why?
Because there is 3 bonding domains, and the carbon you have like S, and then the P orbital, 1, 2, and then you have Is that right?
So you're saying that we start with carbon having electrons in 2s and 2p. If we show the already promoted one, which I think is what you're referring to, we have these 3 orbitals, each one with 1 electron because we have 4 valence electrons for carbon. If we're looking at this, how do we get a steric number of 3 out of these 4 orbitals?
There's 3 bonding domains.
So we have 3 bonding domains around the carbon. So one of them being a double bond, but there's still, what I want you starting to look at today is that when we have a double bond, that consists of 2 bonds. One is a sigma bond, which comes from a hybridized orbital, and there's also a pi bond. So here, when I look at this, I think, okay, there's 1, 2, 3 sigma bonds around that carbon. It means we need to hybridize 3 orbitals in order to get those equally distributed around the central atom. We're always going to start with the lowest energy one first, and then we're going to hybridize 2 of the other ones. So those are the 3 domains, or orbitals, that we're going to hybridize in order to give us 3 identical domains. When we do that, we end up with SPP, or what do we actually call it? SP2, which is a dumb name. There were 3 orbitals we hybridized, so there's still 3 orbitals afterwards, each one with 1 electron in it. But then we also have the 2p orbital with 1 electron in it. Okay, that was not utilized. So by looking at this, we could say automatically from the steric number, if the steric number is 3, we know that it's going to be sp2 hybridized because there have to be 3 equal domains around that central atom. And then we're going to talk about in a second, we're going to go back and revisit what that unused p orbital is, how it's going to help us. All right, so then what is our steric number around that oxygen at the top of the molecule? A couple more seconds. All right, in order to answer this question, what's the first thing that we did? We're going to draw. So we're thinking about the Lewis structure. We know that oxygen almost always has 2 bonds and 2 lone pairs. So we'd go ahead and draw the lone pairs of electrons on there. So the steric number for that oxygen is 3. All right. If we don't think about the lone pairs, we're going to ignore that, and we're going to get the hybridization wrong and everything else. So we have to be able to think about where are the lone pairs in the molecule, how do we count those, make sure that those each count as a steric domain. What's the AXE then for that oxygen?
AXT.
1 bonding domain,
Oh, AX.
2 lone pairs. All right, so double bonds only count as 1 domain. That's how we get our steric number of 3, 1 bonding, 2 non-bonding. All that comes from becoming familiar with oxygen having 2 lone pairs in a bonding domain, sorry. All right, and then if we go back and use the options for our answers above, what's the hybridization for formaldehyde using these 5 options? Go ahead and click in your answer, talk to your neighbor if you're not quite sure. Couple more seconds. All right. Can I hear from Amber? What would you determine the hybridization to be for that?
I said B because the steric number is 3. I always remember that the steric number 3 is usually sp2.
Okay, and I completely agree with you. sp3 because spp, there's 3 orbitals. All 3 of these are going to be identical. So really, if you know the steric number, you know the hybridization. It's as simple as that. Straight across the board. Eric?
But wouldn't it still have two lone pairs?
Correct. It does still have two lone pairs. So how does that work? So if we go back and we look at our 2s and our 2p, how many electrons does oxygen have in those? 1, 2, 3, 4, 5, 6. How many of those are we going to hybridize for sp2? 3 of them. So we're going to hybridize these. Means there's one unpaired, one unhybridized, unpaired electron in 2p. We have sp2, 1, 2, 3, right? Because we hybridized 3, we get 3. And then we have 2p. It's a little bit higher energy. So we still have one electron in that. How many electrons does that put in our sp2 hybridized orbitals? 5 of them? 1, 2, 3, 4, 5. How many lone pairs do we have?
2.
Where are they?
Right there. In the first.
Lone pair, lone pair, ability to make a sigma bond. Joey?
So without even writing that, whatever the steric number is, like if it's 3, then it's always sp2 no matter.
Done. Yes.
So
Savannah?
Why do you only hybridize energy?
So you can go forwards or backwards. So if we know the steric number is 3, we know that we need to have 3 orbitals hybridized. That's going to be the lowest energy, and then 2 of the other ones, right? So it's going to be these 3. We're not going to hybridize the p orbitals. That's not how it works.
So if you went work backwards from the steric number, you would know that. What about working forward?
If we work forwards, I would have to say it's sp2 hybridized. What is our steric number? That's how we work forward. So you don't just come up with a hybridization without knowing what the molecule looks like.
Okay, so you said it would form a sigma bond. I thought like sigma was between two nuclei and pi bond was between 2 p's. So I was
Correct.
thinking there was going to be a pi bond.
Pause. So that's a perfect lead-in to what we're going to do next. So this oxygen can form one sigma bond with a carbon. The carbon, remember, it had 3 single electrons, unpaired electrons in sp2 hybridized orbitals as well. You guys remember we just did that a second ago? So it had 1, 2, 3. 2 of those are going to be to the hydrogens. The third one is going to be make a sigma bond with this unpaired electron. Okay? So we have a sigma bond hidden here between these 2. But then both of them have an unpaired p electron in a p orbital. And so what I want us thinking about is that then on top of the single bond, we have a pi bond.
Oh, so that would be sigma, and that right
Yep.
over there is pi.
So between carbon and oxygen, there's 2 bonds.
Okay.
What are those 2 bonds? Sigma and a pi bond. Both of those exist.
So with a triple bond, which where are we going with that?
We're going there?
2 sigmas and one pi bond?
Nope.
No.
Try again.
Opposite. 1 sigma, 2 pi.
1 sigma and 2 pi. That's what a triple bond is. Okay, so you have in your head, probably 90% of you guys probably have in your head that a double bond is basically 2 sigma bonds, right? 2 single bonds that attach 2 atoms. That's not what it looks like at all. What it actually looks like, this is a poor representation of what it looks like. It actually looks a lot more like what we picture a triple bond to look like. What is the shape of a pi bond?
It's
It's the little loop.
Talk to your neighbors. Everyone shout stuff out. Talk to your neighbors. What does a pi bond look like? One pi bond. Okay, show with your hands, show with your arms. What does a pi bond look like? Right, either this way or this way. That is one pi bond. What's connecting? What's at my fingertips? What's at my elbows? Not the atoms. Yes, Savannah, say it one more time.
P orbitals.
Okay, so a pi bond, the atoms would be between my hands and between my elbows. The pi bond does not connect to the atoms themselves. What kind of bond connects the atoms? These are all covalent. The sigma bond connects the 2 atoms. The density for a sigma bond, sharing those 2 electrons for a sigma bond, that density exists between the 2 nuclei. The pi bond doesn't exist in that space because there's already a sigma bond there. You can't have a pi bond without a sigma bond. Sigma bond exists first in the space between the two atoms, carbon and oxygen. The pi bond, one pi bond, connects the two p orbitals. And remember, each p orbital is a dumbbell shape. So let's take a look at what that looks like. So if we have, let's look at the purple only first. We'll start with the carbon on the left. If we have a steric number of 3, what's the electron pair geometry? Trigonal planar. 3 domains equally distributed in space. Think about a circle cut in 3, right? Can you see how this is kind of trying to draw that three-dimensionally? Those purple ones are all in the same plane. One of the sp2 hybridized orbitals, the one in the middle, is pointing towards the oxygen. What kind of a bond are these two sp2 hybridized orbitals going to make? That's going to be a sigma bond. Each of them has one unpaired electron in it. These other two sp2 hybridized orbitals, they're going to make a bond with hydrogen. Hydrogen doesn't need to hybridize because one s can overlap pretty well. And then each of those atoms has that p orbital that's unhybridized that has one unpaired electron in it. Remember, the shape of a p orbital is like a dumbbell.
And since it has a double dumbbell, it's kind of like because it has both ends, it's more like a barbell, I would think. It has to connect on both ends of the barbell.
Yeah, and so if we're looking at this p orbital, I want you thinking about the PhET simulation. Remember how when we moved the domain of electrons, they would repel each other, and that's where they'd end up in space, because you'd move it closer to another electron domain, it would repel back, and they'd get as much space as possible from each other. If we think about the sp2 hybridized orbitals as trying to get as far away from each other as possible, they're going to be trigonal planar. But then if we take this p orbital that has a domain on the top and the bottom, there's no way that we can line that up within the sp2 hybridized plane. The only way for it to minimize repulsion with all these purple lobes is to go 90 degrees to it. Lloyd?
So the blue p orbitals, those are signifying what the pi bonds, where the pi bonds would meet?
We're going to use those to make a pi bond, correct.
Okay.
And let's just make sure we're using the right terminology. This on the left, the blue, is one p orbital. There's not multiple p orbitals. So when you said p orbitals plural, I hope you're referring to the left and the right. Each have one, because remember, p orbital is not, it's symmetric on both sides of the nucleus. So then, if each one of these has one unpaired electron, we can make the sigma bond in the sp2 hybridized domain here between the two nucleus, and then we can make one pi bond with two unpaired electrons. And I showed this briefly at the very end of the last class, but this is kind of what it looks like. So what's in, let's look at the oxygen. What are the 3 sp2 hybridized domains? What do they have in them? The oxygen has
2 lone pairs.
Remember when we drew it out, there was 2 lone pairs, 2 out of the 3, and then the other one has a single electron that now is sharing carbon's one of carbon's unpaired sp2 hybridized orbitals electrons, making the sigma bond between the two nuclei. P orbitals are the top and the bottom, and they end up bridging over and making a pi bond, a single pi bond.
So with the 2 sp2 orbitals, they're kind of like blending together and making an area in the center where it's higher probability of finding the electron. But with the p orbitals, are they combining together?
So both of the sp2 hybridized orbitals, this is maybe, so your point is that the pi bond looks like it's kind of merging of the 2 p orbitals, and the sp2 looks like they're still separate. That's probably inaccurate.
Okay.
That usually when we show a bond, a sigma bond between 2 atoms, it's just a high electron density between the 2 nuclei. I think they left the overlap here to kind of show where they came from, which I don't know is the best visual representation. It's a good question. The major thing I want you guys to look at is, remember when we draw formaldehyde, we draw a carbon, 2 lines, and an oxygen. Why is that a bad representation in some ways? I want you to talk to your neighbor. Why is that an insufficient description of an actual double bond? So what I'm asking is, why is that a less accurate version of this? What's the big difference?
Can I disagree and say, is
Okay, can I hear from a new voice? What is the major limitation or the biggest difference between those two ways of representing a double bond? Christina?
I don't know if I'm right, but you don't know if it's a double bond or single bond representation.
Well, so we use the common descriptor that that is a double bond. But once we actually know what a double bond looks like, what's the biggest difference? Savannah?
It looks like a triple.
What looks like a triple bond?
The one sigma, or the one sigma bond and the one. I mean, it looks like there's three, but you know that the dumbbells, there's two of them, and they both connect on each side, so it makes it look like there's three bonds.
So if we were to accurately draw what a double bond actually looks like, it would confuse people who don't really understand what's going on, and they would think it's a triple bond. Right? This is kind of what a triple bond might look more like, having three lines connecting them, that this blue is one pi bond, and the purple is one sigma bond.
So what about triple bonds?
We're getting there. We're getting there. Pause. Okay, so the representation at the top is for people who don't need to know the quantum description to understand where electrons actually exist between atoms, all right? There's limitations to the way that we draw Lewis structures. So what I want you guys, as educated scientists, to be able to describe is what is actually hidden within that drawing of a carbon with two lines to an oxygen, or any atom that has two atoms that have two lines between it. So let's then go and let's think about a triple bond. And I think we have our learning objectives before that. Oh, let's make sure that we're on the same page for all this before. We'll do a checkup. How many single bonds do we have in this molecule? Couple more seconds. We are split almost down the middle. Talk to your neighbor. Someone's missing something. Okay, can I hear from a new voice? What might someone have missed? Go ahead.
Someone might have missed that just because it's a double bond, I mean, it's still a sigma bond, even if it's a double bond, because you have one sigma and one pi bond in a double bond, and someone might have missed that thinking that it's just a double bond, so it doesn't count.
Great. So the mistake you're referring to is if we said the answer is two sigma bonds. One from each carbon and hydrogen, because a single bond is a sigma bond. The thing that people might have missed is that any double bond is a sigma bond and a pi bond. So this molecule has three sigma bonds.
So would it be, on a test, if you ask us how many single bonds are there in whatever?
That would be a bad question to ask how many single bonds there are. Right. I would ask how many sigma bonds there are.
Okay, just double checking.
And that is on the test, on a big molecule. So we'll practice a bit more. So do we need to answer this question? How many pi bonds are there? So Moab, your question, you're specifying the single bonds up there in quotes?
Yeah.
Yeah, so that would be on a test a bad way to ask this question. And so what I was doing was I was trying to elucidate that a sigma bond is what we're going to be referring to them as going forward. Very good question. Okay, so we have one pi bond in this molecule. That's pretty easy to tell. We'll get into a little more complicated stuff in a second. All right, so let's pause for a second. I got two questions to ask you guys. One question is about today's class. So I printed out an activity that would get us starting to think about balancing equations, because your lab next week is going to be balancing equations. You guys have been doing that a little bit in your precipitation lab, your types of reactions. Next week is going to be more. I think I'd rather spend a bit more time looking at big molecules, hybridization, and that kind of stuff. I want to get your feedback on whether we spend the rest of the class on that or not. If we do spend the rest of the class on that, I'm going to need you guys to work on a little bit of this before class next Wednesday. And the amount is going to be completing Model 1. Let's do a clicker to see if you guys are willing to do that. Okay, I'm letting you guys decide how we spend the rest of class. If we spend the rest of class working on structures, molecules, hybridization, all that kind of stuff, you guys are going to have to complete it to Model 1 before class. That means we're going to hit the ground running Model 2 in class next week on Wednesday. Okay? So go ahead and click in your answer. Yes, you're okay doing that. I'd say it would probably take about 20 to 30 minutes. You're welcome to do it with other people. You're welcome to do it over the weekend. You're welcome to do it after the exam, whatever you want. But if we decide to do this, you have to complete activity Model 1 before next Wednesday's class. No, that we start working on this and we do this in class today instead.
Will this model be on the exam?
No, balancing equations is not in the exam. Okay, has everyone clicked in? The screen's frozen. Hybridization will be on the exam. All right, has everyone got a chance to click in? Everyone seen the answers? A is yes, B is no? Sorry, I'm sitting in front of you guys. Okay, so there's 3 people who don't want to do this. With the majority of class 1 and 2, I'm going to go ahead and spend the rest of class today working on understanding molecules and doing that. Okay? So these are the learning objectives for last class, and I had them up here. There's another set for that activity. So the 2 things I need you to do, I need you to complete Model 1 by Wednesday, or if you have lab Tuesday, I would suggest doing this before your lab on Tuesday. The second part of it is you have to bring this to class. I'm not printing this out again. It's too much to print out an entire packet again, okay? So let's go ahead and spend some time thinking about pi bonds and hybridization. Thank you for the input. Oh, one other question I have is office hours. I'm basically available the rest of the day today, and my office is very small. Can fit, 4 people maybe in there? I do have a very large space over in ETAS that I could use and be available to meet with students, but it's a little bit harder to find. If you were planning, basically we would walk through the kinds of things we're doing today in class. If you wanted to stop by office hours, we'd work in small groups. Raise your hand if you're interested in coming by office hours and practicing this kind of stuff if you have availability to do that. Based on the number, I will determine what location to do it in. Okay, so 10-ish. So my technical office hours are 1 to 2:30. Aside from grabbing lunch between 12 and 1, I'm pretty much going to be hanging out in whichever office we decide. So since the numbers, there's only about 10 people that raise their hands, I'll probably stick with Science Lab 273 because it's easier for you guys to find. And if you come anytime besides 12 to 1, I'll pretty much be there. Okay, so feel free to stop by, grab someone else from class to come by if you want. We can work through problems. All right, and I would love it especially if you didn't do as well on exam 1 as you want and you really want to kill exam 2, if you work through the kind of stuff we're doing here and you do that for half an hour together in office hours or 45 minutes, then you will be very well prepared for the exam on Tuesday. So even if you didn't raise your hand, please make time to come by.
Will you be there a little after?
Yeah, I'll be there from 1 until 5-ish. So that's where I was like, do I do it in the bigger room, the smaller? I'll do it in the smaller room, but we'll figure out how to make it work. Okay. How many sigma bonds do we have in this molecule called acetylene? Go ahead and click in your answer. And then you can guess what the next question is. You're thinking of acetone? Acetylene is... acetylene is used in torches for welders. An acetylene torch uses this as a gas. It's very flammable. All right, not everyone is agreeing on this. What are you guys thinking? Can I get a new voice? New voice. Someone who hasn't talked yet. I love the enthusiasm. Mohammed?
I put 3.
Why 3?
Because, like we were talking about how, when you talk about sigma bonds, and there's a triple bond right there, the triple bond is just 1. And there's a bond going on between carbon and hydrogen on each side, so that's a 3 bond right there.
I agree. Sigma bond on either side, those are really obvious. And in the middle where we have a triple bond, that's 1 sigma bond. So then let's think about, I don't know if this is the next question that pops up. How many pi bonds do we have? Go ahead and click in your response. Couple more seconds. All right, the class is in agreement. We have two pi bonds here. How do we get around each carbon? How do we get 2 sigma bonds and the ability to interact with another atom with 2 pi bonds? Talk to your neighbor. What do we know about the hybridization of that carbon based on that information alone? Think about the steric number. Think about how many orbitals we'd have to hybridize. What would be left over? Dawson looks enthralled, so I'm going to ask him to explain his thought process. What information do you gather about that carbon based on the fact that it has those 2 sigma bonds and 2 pi bonds on it?
I have no idea what to think, so I don't know.
Someone want to help out? Shania, what are your thoughts?
Sinuses.
Joey?
So we're talking about the carbon, right?
Correct.
Whatever. So there's 2 of them, so wouldn't it be SP? Would be the
There's 2 what?
domain areas?
Yep.
Whatever that
So
is.
steric number is 2.
Yes. So from the other one, we were SP2, which means, or we had 3 domains, so we were SP2. So we got 2 of them now. Let's just go down 1 more. At SP, so we have that.
Then what's left over? If we only hybridize 2 of the orbitals,
You have to have 2 hybridized orbitals because those are the sigma bonds. And if you have 2 pi bonds, you have 2 extra. So
great. So I love the thought process. So you said what's the steric number? That's going to determine how many sigma bonds we need and how many hybridized orbitals we have to have in order to do that. So this carbon has 2 domains around it. So we're going to do sp hybridized. We have 4 electrons, so 2 of them are there. And then we only hybridize 2 of the 4 total orbitals. That means that 2 of the p orbitals are still left unhybridized. And we have 4 electrons total, 1, 2, 3, 4. So we have 1 electron in each of the p orbitals that's unhybridized, which can make 2 separate pi bonds. Let's think about what that looks like now. What's the molecular shape if we have a steric number of 2? Linear. As far apart from each other as they can get. So where are we going to put our 2 p orbitals? Go ahead, Joe.
it's going to look like a plus, straight up and down.
Okay, a plus if we're looking at it this way. So is one this way, one this way?
No, one will be straight up and down, and then facing at you and going away.
Okay, so if we look at it down the HCC bond, if we're to look at it down down the length of it,
Yes.
then it would be a plus. Exactly what you're saying. 1 p orbital is going to be up and down. 1 is going to be perpendicular to that. And that's going to give us the most spacing we can possibly get for each one of those domains. The 2 sp hybridized orbitals are in the line of the molecule. That means that the other two are going to have to be across. So let's take a look at what that looks like. So we hybridized two of those, two of the total orbitals. We have two left over. Sorry, a lot of text on this. So we're just looking at the two carbons in acetylene, and both of them had the same geometry, same steric number, so we did the same thing on both. So the p orbitals, or sorry, the sp hybridized orbitals are in the line of the molecule. What kind of a bond is this sp going to form with this sp? We got a sigma bond right here, and then we're going to have the p orbitals like a cross if you're looking at it from down the line of it. So then where are our pi bonds going to form? Someone want to draw it on the iPad? Someone want to try to draw it? Logan, is that you? So describe when you're doing one, and describe when you're switching to the other.
So, two carbons.
You can draw it on the one that's already there.
Oh, okay. So it's going to be like the top and the bottom.
Okay, is that one or two pi bonds?
One.
Great, that's our first pi bond. Where's the second one?
And one's going to come toward us and one's going to go behind us.
Okay,
right,
just
just
try
like,
to draw it. It's a bit tough. One in the back, one in the front.
just like that. Yeah.
Thank you. All right, and then to make this drawing look like poo, we have a fancy version of it. I appreciate I want you guys to try to visualize how these things work, and if you just see this, I don't think it's necessarily going to give you the same input as thinking about what it might look like. So you can see there's one pi bond back in the front, one at the top and the bottom, two pi bonds. Sigma bonds still exist between the two nuclei.
This one, when we're doing that whatever simulator thing, you told us that the double bond is a little bit bigger than the single bond because it's got that.
So there's a couple reasons why. So I love what you're thinking about. You're thinking about when you have a double bond versus a single bond, what's going to have more repulsion in the simulation? And more repulsion comes from a couple things. What's the length of this bond when it becomes a double bond? Does it become shorter or longer? Double bonds are longer than single bonds? All right, they're shorter. So that means it brings that electron density in a smaller distance between the two. And the second component is, once you have a pi bond, it does make it wider as well. So you have now, how many electrons do we have between these two carbons? How many total electrons exist in this general vicinity between the two carbons? 6 of them. So that's a huge amount of electrons, and they take up more room because it expands on both sides of the internuclear space. Sigma bond is just between the two nucleuses. One pi bond is in between and a sigma bond between and the pi bond, and then a triple bond is 2 of those pi bonds. So the volume of space kind of that it takes up is a lot greater where those electron domains are, which will repel the other groups more. Great point. Kiana? You have a question? You want to come back to it?
Well, I'm confused on, like when looking at the one at the top, the equation at the top, they have one pi bond, and there it has 2. So I was confused how that came.
What do you mean? One pi bond? Where are you pointing at? Okay, so thinking about the process, you can really go forwards or backwards. If I say it's sp hybridized, you're going to have to be able to tell me how many sigma and pi bonds there are, or it can make, how many unhybridized p orbitals, how many hybridized orbitals there are, and then we can figure out based on the number of electrons that populate those, what the electron pair geometry and molecular shape are. That'll determine the AXE. So if we go back and we talk about the representation and how it's kind of not as full, how would we really accurately draw a triple bond if we were to describe where the pi bonds are in space? What would it look like?
You'd have the one purple line directly between them, and then you'd have 4 curved blue lines.
Yeah, so this would be one pi bond. We would have another pi bond that wraps around, so we'd have 4 blue lines between each carbon. But I don't want us to think that there's 4 bonds, 4 pi bonds, right? There's only 2 pi bonds, but each pi bond is on both sides of the axis. Which one do you think is going to be harder to break? A sigma bond, or let's say a single bond versus a triple bond, and why? Talk to your neighbor about that. Which one is going to be harder to break? Single or a triple bond, and why? All right, pull up your fingers. A single or a triple bond, which is going to be harder to break? All right, can I hear from someone who's been quiet so far, who hasn't said anything yet in class today? Why do you think the majority of people in this class said a triple bond would be harder to break? Why might that be? Tyler.
Don't make eye contact, James.
I wouldn't call on you whether you made eye contact or not, unless you shook your head. People who shake their head, I usually don't call on them.
That was my intention, so I went single, just because it's opposite what I figured.
Okay? Someone else want to help out? Someone who hasn't talked yet today. Why is it that a triple bond might be much harder to break than a single bond?
There's more stuff there.
There's more stuff there. Trey, you want to elaborate on that?
Just more electrons shared.
There's more electrons shared. Why are the electrons being shared? Let's think about stability. Go ahead.
Because you have the hybridized, whatever, you have a little shelf area. So to be stable, they have to have both of them. And so to get
Why?
both of them, they have to share.
Okay, so in order to fill their orbitals and have paired electrons, they need to participate in a bond, right? Why do they need to fill their orbitals? To be more stable, great. They typically strive towards 8 valence electrons. Why?
Because they're alone.
When you are alone, you try to grab someone else to hang out with, which is true. Think about back to quantum, right? We talked about in quantum.
Just the lowest energy state.
Lowest energy state is light. What kind of element on the periodic table?
A noble gas.
All right. So the octet rule, remember, octet or duet rule, is all about trying to achieve maximum stability with electron configuration. Carbon only has 4 electrons. If it has 4 more that it gets to share from others, then it appears that it has a noble gas electron configuration, and it is more stable. So let's think about the energetics. I want you really wrapping your head around the energetics of that. If it's more stable in that triple bond, you're going to have to break multiple different ways in which it's interacting. And instead of that stability coming from 4 different bonds around carbon, it's coming mostly from 1 bond. So that one interaction is a huge amount of its gaining stability. So to undo that is going to take a lot of energy.
Yeah, but it also releases a ton of energy. Acetylene can explode.
So acetylene is flammable. We have acetylene torches. That's what a lot of welders use. So if you do give it enough energy to break that bond, a huge amount of energy is released to form carbon dioxide and water.
Whenever, on our homework thing we did the other night, whenever you just showed us a picture, can you explain that? Like, I understand this, but you just showed us a diagonal picture and said, all right, tell me if this is 1s, whatever it was. I didn't understand it.
Hybridization?
Yes.
Okay, so I think what you're referring to is if we see the number of hybridized orbitals, basically what it would be doing is only showing you the purple. So if you saw 2 purple orbitals like this, what would the hybridization be automatically? How do we go and look at 2 hybridized domains? How do we determine the hybridization of that? Steric number. We know the steric number would be 2, so it has to be. If we saw 3 lobes that are trigonal planar, what hybridization is that? That's sp2 because there's a steric number of 3. Does that help? So if we see tetrahedral, it's going to be sp3. What about if we do a steric number of 5? So we had a number of molecules in our lab that had a steric number of 5. Steric number 5 means we can't do S and P's. There's only 4 of those. So we have to have D. Can we, let me see it, can we do this?
Wait, 2?
Can we hybridize, I'm not going to draw on the electrons.
Wait, 2D?
What is Jackson unhappy with? Can someone help out?
Their D orbitals, or D shells, only start in period 3.
So can we have a steric number of 5 if we're in period 2? No way, we can't do it because 2D doesn't exist. So if we have an element in period 3, 4, 5, 6, we have d orbitals are now available. And we can spill over electrons into the empty d orbitals. Remember, if we're talking about sulfur, sulfur has electrons in 3s and 3p. Are there any electrons in 3d yet?
No.
So we can overflow electrons. We can exceed the octet rule because we can put more than 8 electrons in because we have a vacant d orbital in that shell. Right? These are the ones that start filling d orbitals. So those are empty when we think about sulfur, phosphorus, chlorine.
What would that look like if you're filling in the electrons on whatever that's called?
Filling in the electrons, what do you mean? So if we're thinking about sulfur, for instance?
Yeah, so it has...
So how many valence electrons does sulfur have?
6.
All right, so 1, 2, 3, 4, 5, 6 would be the normal electron configuration of sulfur. If we're going to form 5 bonds, though, we have a lot of paired electrons that would not necessarily be useful to us. So we would have to promote an electron first, and then we could hybridize those. If we have a steric number of 5, this is what we do. What if we have a steric number of 6 around an element? What would we do?
You take the 3s
Slow down, slow down, slow down. I want people to get a chance to think. So what would the difference be if we had a steric number of 6 from what I just drew here? Lori, what are your thoughts? Yep, we could promote the ones in the S up to D, and then what would our hybridization be to get a steric number of 6? So let's think about sp3d. 1, 2, 3, 4, 5 orbitals. So if we promoted this up to the D, we'd have to hybridize how many orbitals to get a steric number of 6? 2 of the Ds. Yeah, Moat?
So why didn't you promote the 2 electrons in the s orbital when the steric number was 5?
In this case, it's not really as important. I just want to show that we have an electron, unpaired electron in D, because once we hybridize all 5 of those, then we populate them with the electrons that we have. Okay?
So generally you would promote the one in the s orbital to D? Right?
Promoting to D, we'd probably promote the one that requires less energy.
But wouldn't you have to promote the one from S to make it on 5 times? Because that's
Oh, to get to steric number 6?
Yeah, because
yes.
that's alone pair.
Right, so the green circle is for sp3d, not sp3d2. Correct. All right. So let's go back to Abilify. Let's start picking out hybridization of different atoms. We're just about out of time. So we're going to do 2 of these right now. I'm telling you, this is the best practice you can possibly do. Get a big molecule and identify all these things. In addition to looking at any atom and determining what the hybridization is, these are other things we talked about that you need to be able to do. Should we just ask how many pi bonds are in this molecule? Try to decide that really quick. All right. How many pi bonds? Can I get a volunteer? Jason. Okay, which three?
Hydrogen, nitrogen, carbon, and nitrogen, carbon.
You're talking about steric number of this guy. Sorry, I was asking a question that's a little bit off from that. So if we look at the entire molecule, how many pi bonds do we have? Different question. Ruby? 7. 1, 2, 3, 4, 5, 6, 7. Okay? And then at each time we have a pi bond, we know that there has to be at least one unpaired p orbital unhybridized. This oxygen has a p orbital unhybridized, so does this carbon. That tells us it's sp2 or sp. These are the kind of steps I need you guys to go through. So please do come by my office at some point today if you want to work through this. I really advise you to make sure you know what the atoms are, what the bonds are, what the lone pairs are, everything related to a big molecule, and then you will crush the exam on Monday. I want to see everyone getting 90% or higher in the exam Monday, all right? The way that you reflect on what your learning is fantastic. So I think you are also getting good grades. That's not what you are. The process, the ability to help other students move along that thought process. I think you'd be really good. You don't keep for sure. We'll get the schedule on later.